So we are going to continue with the chemistry of the elements, part 3. So let's see what is the outline for this part 3. So here we will discuss about how to identify the periodic variation in physical properties. In this part 3, we focus on effective nuclear charge, or known as Zeff effective, and second one is the atomic and also ionic radii. So, all predictable trends actually influenced by 3 factors. Okay, first one is the energy level. So, higher energy levels are further away from the nucleus. And second one is the charge of nucleus, or what we call nuclear charge. Okay, so what happened here? More charge will pull electrons in closer. Okay, means positive and negative will attract each other. And third one is the shielding effect. So what do you remember, or what do you know about shielding effect? Okay, so what is shielding effect? Shielding effect is actually the electron, okay, on the outermost energy level has to look through, okay, for example here, this is the electron, okay, on the outermost energy level, okay, has to look through all the other energy levels here, for example here, here and also here, to see the nucleus. So it means here it is actually related to the attraction of the electrons on the outermost energy with the nucleus. Okay, and if we have the second electron, okay, this electron also has same shielding effect if it is in the same period. Okay, so here, okay, shielding effect is actually related to the size. Okay, the larger the size, or the larger the size of the atom, okay, the higher the amount of the shielding effect. Okay, all right. And then so we go to the atomic size. Okay, so how to measure the atomic radius? Okay, so here from this diagram, okay, this is actually half the distance. Okay, this is the radius, okay, the r, okay, this is half the distance between the two nuclei, okay, of a diatomic molecules. Okay, half of this is radius, one radius, and this is another radius. Okay, right. And then what do they influence based on the atomic size? First thing is the energy levels, and second one is the shielding that have an effect on the group. Okay, and nuclear charge has an effect on the period. So energy level and shielding actually here, okay, focus on the size. Okay, if you have higher energy level, it means that you have bigger size. If you have a large amount of shielding effect, it means that you have a large size. Okay, and second one, okay, nuclear charge, okay, actually has an effect on a period. So it means that you need to determine, okay, the charge of the positive or negative, alright, of ion. Okay, alright. So for energy levels and shielding effect, okay, give effects on the group, while for the nuclear charge, okay, give an effect on the period. Okay, so a group, as you know, okay, is actually from top to the bottom. Okay, and the nuclear charge effect on period. Period means that from left to right of your periodic table. Okay, so other than that, other than atomic size, okay, we go to the second one. It is actually the effective nuclear charge, or known as Zeff effective. Okay, we usually write it down as Zeff effective. Okay, so what does Zeff effective mean? Okay, it is actually a positive charge felt by an electron. Okay, alright. So how many positive charge actually that electron have? That electron has. Okay, so the formula in order to determine the Z effective is Z effective equals to Z. Okay, Z it is actually actual nuclear charge. Okay, minus sigma. Okay, the sigma here is the shielding or the screening constant. In this case, it is actually the core electrons. Okay, alright. So Z minus number of inner or core electrons. Let me give you one example here. Alright. For example, we have a sodium with actual nuclear charge of 11. Okay. And then it has 10 core electrons. Okay. So the Z effective here is 11 minus 10. Okay. It will give you 1. Okay. So the radius for sodium here is 186 ppm. So this is in ppm. Alright. And then another example, let's say we have magnesium 12. Okay. The core electron is 10 and the Z effective will give us as 2 and the radius is 160. And then here this is 11, 12, 13 and this is 14. So as you can see here, this is actually across a period, okay, from left to right. So as you know, from left to right, it will give you a decreased number of atomic size, okay, of an atom. Okay, so what happened here, as you go from the sodium to magnesium and then aluminium and last but not least is silicon here, what happened to the radius? Okay, the radius of these atoms are decreasing, okay, because of the increasing of the Z effective here, right? So actually the Z effective give an effect, okay, to the size of atoms, right? And then so this is the overview of the periodic table in terms of the Z effective, okay, from left to right or across periodic table. Okay, we have increasing of Z effective as I have explained before this, and then from bottom to the top of the group, okay, we have increasing of Z effective because, okay, from the bottom to top we have the decreasing of size of the atom. Okay, alright, so what happened here, size becomes smaller. Okay, and here also we have size, small size. Okay, so the Z effective actually related to the size of atoms, okay, in periodic table. Alright, so here other than that, okay, because of the size, okay, we can relate to the attraction of the electrons with the nucleus. Okay, as you across the periodic table, okay, we have increasing number of electrons, okay, and then what happened here, the core electron will become closer to nucleus rather than valence electron. So what happened, the core electron actually shield the valence electron and the valence electron shield each other. So this is what happened, okay, when we actually from across the period or actually from bottom to the top of the group. And then other than that, here we have, okay, when we move down the group from top to the bottom here, the Z effective decrease, okay, the Z effective decreases, okay, because of the number of the orbital increases. Okay, so when we have large number of orbitals, so what happened to the size? The size of the atoms will become bigger because of large shell increases. So valence electron are added to these large shells. Okay, so what happened to the static attraction between the nucleus, okay, with the valence electron, it will become decrease, okay, or it will decrease, okay, when we have additional number of orbitals. And then another, here we have example, okay. Here the question here is, which element's outer shell or valence electrons is predicted to have the largest effective nuclear charge. So here you need to use the formula, okay, where the Z effective, you need to use the nuclear charge, okay, minus with the core electron, and you will get the Z effective, okay. Alright. And then other than that, we go to the trends, okay, of the atomic size in periodic table. Okay, so the atomic size increases, okay, down a group, okay, because we have the number of electrons and field electron shell increases, the number of orbital increases, okay. We usually refer this one as shell as N, okay. And then electrons are found further away from the nucleus because of the size, and so what happened, the atomic radii increase, okay. This is where we have the example for group 1, okay. Group 1. And then second one, we have atomic size for period trends, okay. Across the period from left to right, okay, the atomic size decreases, okay, here. This is where we have the period 2, okay, from left to right, okay. And then, okay, so let's say the electrons, okay, electrons are in the same energy level, okay, and unshielded towards attraction by protons, okay. So these protons are actually being added to the nucleus and creates, okay, a higher effective nuclear charge. That's why we have decreasing trend of size across the period. And then another factor is we have a stronger force of attraction pulling the electrons closer to the nucleus, so the size will become smaller. So here, this is the summary of the the summary of the atomic radii. Okay, here based on the it is actually a cross period, okay, from lithium to fluorine, sodium to chlorine, potassium to bromine, and so on, okay. And what can we see here, okay, from left, okay, this is all from the left group, group 1, from left to the right, okay. So here we have group 17, okay. As you can see from this diagram, okay, we have a trend of decreasing size of atomic here, radii. And then, okay, so we have discussed about the atomic size, and what about the ionic size, okay. So this is what I have explained to you in part 2, okay. What happen if you have parent atom and also anion and also cation, okay. So for the anion, negative ions, they are always larger than their respective atoms or their parent atom, because we accept, or the anions actually accept or receive electrons, okay. So what happened here, the electron repulsion forces them to spread further apart, and here protons cannot pull the extra electron as tightly toward the nucleus, so it will become bigger, okay. And for the cations, positive ions, they are always smaller than their parent atoms or respective atoms. Why? Because there is less electron repulsion, because we remove electron, okay, and the protons will outnumber the electrons, okay. So maksudnya proton more than electron, so this proton can pull the fewer electrons toward the nucleus more tightly, and the size will become smaller. So this is the ion group trends, okay. So this is each step down the group. So what happened here, we have additional number of level or what we call orbital, and then ions therefore get bigger as you go down because of the addition of energy level, okay. And then we have ion period trends, okay. So this is across period from left to right, the nuclear charge increases, so they will become smaller. And then here, okay, please notice, okay, the energy level changes between anions and cation. This is what I have explained last part 2, in part 2, okay. What happened, why we have nitride, okay. So here nitride, NiTRIDE, this is -3. It has the largest size, okay, among all these ions, because it receives 3 electrons, while for the oxide only receive 2 electron, and fluoride receives 1 electron. While for the cation here, they remove electron. The larger the number of electron being removed, so what happened here, the size will become smaller. Okay, so I have one quiz for you here, so please try to answer this quiz. We will discuss during class. And then, okay, what happened to the size of isoelectronic ions? Okay, this is what I have explained before. Iso means similar or the same. Okay, so what happened here, they have similar number of they have same number of electrons, okay. So what happened here, they will have same electron configuration, but okay, please bear in mind, okay, it doesn't mean that they need to have same size, okay, because cation will become smaller and anion will become bigger than their parent atoms, okay. So here, alright, positive ions that have more protons will be smaller, okay, because we have larger attraction between protons and electron, and also the nucleus. And here, okay, so these are the example of the size of isoelectronic ions, okay. And then I have another quiz for you here. Please answer this one. We will also discuss this one during our virtual class. That's all for this part 3. I hope you guys enjoy my video, and I think that's all for this part 3. I hope you can spend some time to study the video. Okay, so guys, I'll see you guys in part 4. So last but not least, please like and comment, and also subscribe my YouTube channel, and I will see you in part 4. Bye.